Good morning and welcome to week 1 of Stats 243B. This is just a quick video. I'm going to try to keep it relatively short, hopefully around 7 minutes, where we can talk about what the reading is doing this week and what we're hoping to learn. So first of all, this week is not really in your textbook. This is kind of a review week, talking about continuous distributions from last term. So this continuous distributions play a huge role in this entire term. So I just want to kind of review them. In a discrete distribution, you have like a set number of things, like the sides of a dice, for example. There's a 1, a 2, a 3, a 4, a 5, and a 6. And you each one of these things has a chance of happening, right? And you just end up counting how often they happen. Each one happens 1 out of 6 times, right? So this is a discrete model. In a continuous model, I want you to think of it more as an area model. So the discrete is more of a counting model. You count how many times things happen out of total. This is more of an area model. It's more like you're playing target practice and you want to know what's the probability that you hit the bullseye, right? That is the difference between the two, right? And continuous distributions, like I said, they play a huge role in what we're going to do for the rest of this term. You will remember some of the continuous distributions that we had before. The main one was the normal distribution. It looked like this. Right? It had 2 parameters that you needed to know what the curves were. You needed to know where the mean was in the middle and what the standard deviation was. Those were the 2 things that you needed to know. And then if you had those 2 things, then you knew everything else about this curve, right? This is called a normal distribution. And this one played so prominently because we learned at the end of last term that if you had a sampling distribution, if you looked at, regardless of what the whole population looked like, if you took a sample and calculated the means, then the means fell into a normal distribution, right? So this is the first one of them, right? But in this normal model, we also talked about last term uniform distributions. And that one looked something like this. It was essentially a rectangle. And the 2 parameters that you needed for a uniform distribution were A and B, a starting point and an ending point. Right? What all these distributions had together was that, or what all these distributions have in common, regardless of what their shapes are, is that the area under these distributions, if I look at this area under this distribution, again, we're thinking of this as an area model, because it has all of the possibilities, the areas under these distributions are always equal to 1. The total area is equal to 1 because it's 100% of the probability, right? So the total area is always equal to 1. So a lot of our work over the next term is going to be trying to figure out one of 2 things. One, the first thing is, what are the cutoff points? Right. If I'm given 2 cutoff points, then what is the area in between, or the probability? That's one question that we will answer. The other question that we will answer is, if I'm given a particular probability, if I'm given a particular area, also known as probability or percent of the total, what is the cutoff point? Okay. So those are the 2 types of questions that we're going to answer throughout this term. Okay. In this first week, I just want to familiarize you with several different continuous distributions. The first one we'll work with is a normal curve, which you're already familiar with. There's also a uniform. There is a t-distribution. Right? The t-distribution looks an awful lot like a normal curve, right? Right. The parameters that you need for t is you'll need to know its degrees of freedom. Which will always equal 1 less than your sample size. Okay. So it's always centered around 0. And then the shape of the curve, like how thick it is or how skinny it is, will be based on your sample size. So if you have a sample size of 99, then your degrees of freedom is 98. If you have a sample size of 10, your degrees of freedom is 9, so on, right? This is called a t-distribution. We'll also look at a chi-squared distribution. Chi-squared distributions are made up in a really interesting way. Chi-squareds are what happens when you take the points of a normal curve and you square them, and then you add them to each other. And depending on how many times you add them to each other, that's also called the degrees of freedom. Because you're squaring them, because you're taking something squared, it can never be negative. So this is our first distribution that starts at 0. And then it's a family of curves that looks like this. Right? How tall and skinny it is based on how big your sample size is. The bigger your sample size is, the more it will kind of lower out and even out like that. The smaller your sample size is, the steeper it will be like this. The area underneath this curve is still always 1. Your degrees of freedom is the parameter that you need. And again, that's based on your sample size, which will be n minus 1. And then the final one that we'll look at this week, is called an F distribution. An F distribution is what happens when you divide a chi-squared by a chi-squared. So if you take a chi-squared divided by a chi-squared, you take something that's positive divided by something's positive, still going to be positive, right? And then it's going to have a slightly different shape than this, but still the same idea. It's going to go up and kind of come down based on its degrees of freedom. Because you're taking two chi-squareds and you're dividing them like this. There's a chi-squared divided by a chi-squared giving you this kind of shape. Again, this one has 2 degrees of freedom, or 2 parameters, 2 degrees of freedom. One from the numerator and one from the denominator. Right. So like it will give you in the problem the 2 degrees of freedom. They'll call it DFN for degrees of freedom of the numerator and DFD for degrees of freedom of the denominator. Right? So let's take a quick look at real briefly, like how do we use this, right? You know, like what would we do? Let's say I want to know, let's say I have a chi-squared distribution. So I have a chi-squared, and I have a sample size of 17. And I want to know what's the probability that I'll call it just little u for now, in this chi-square distribution is greater than or equal to 10. So let's think about what's going on here. We have a chi-square distribution that looks like this. I want to know if this is 10, what's the probability that, what's the area, sorry about that. What's the area greater than 10? I'm looking for that area right there. Right? So I do this the same way we did this last term with the normal distribution. I go to, on my calculator, I choose the distribution button. So dist. And then I look for inverse chi-squared. I'm sorry. I look for chi-squared CDF. Right? I look for that number, and it's going to say, what's your lower limit? And I'm going to tell it 10. It's going to ask you what your upper limit is, and I'm going to tell it I want a really big number, like infinity, way up here, but I don't have an infinity button on my TI-84, so I'm going to put in just a huge one with lots of zeros in it. And then it's going to say, what's your degrees of freedom? And I'm going to look up here and say, wow, that is 1 minus that, so that's 16. Okay? And then I hit enter, and it's going to give me the answer that I want. I can do the same thing in Minitab. I go to cumulative distribution. Then I put in the parameter of degrees of freedom is 16, and it'll say for like an exact value or whatnot, and I'll put in 10, and it always gives me the left tail and not the right tail. So then I'll have to take that answer and go 1 minus my answer, and that will give me what I need. All right. Well, that is as much as I'll chat about today. Of course, if you have any questions, please let me know. And I will try to do a couple sample problems from your homework and post that video as well. Thank you so much, and let's make it a great week.